All right, so I split the videos in the middle of a question that actually refers to an earlier question, but that's all right. So it's this number 11 for AP1, Lesson A, Units 6 and 10. This is the one on oscillations. The last video ended at number 10, which was this situation. A pendulum going this way and a spring with a mass going up and down. And it says, this question says, which is true for both spheres? And right off the bat, we stumble across the right answer. And that's because it says the maximum kinetic energy is attained as the spheres pass through the equilibrium position. That is true of all simple harmonic motion. If something is in simple harmonic motion, it is going fastest as it goes through the equilibrium position. Think about it. The equilibrium position for a pendulum is at the bottom. That's when it's going its fastest. For a spring, it's right in the middle of its two amplitudes, and that's when it's going the fastest. So A would be our right answer here. All right, displacement with respect to time for a particle moving in simple harmonic motion is given by 5 cosine, blah, 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 where x is in millimeters and t is in seconds. If the particle starts at 5 millimeters at t equals 0, what time does it first pass through the equilibrium position? All right, this ought to be interesting. So let's see. The period, so there's our particle. So we'll treat it like a spring. So here's our particle, like a horizontal spring situation. So the spring is compressed here, equilibrium here, stretched out here. And it's going back and forth between these two. And it starts, the amplitude is 5 millimeters. And it starts, we'll say, out here. And they let go. And when does it first pass through here? Well, let's do it in an amount of a period. One full period, we'll do in green. One full period would be from here all the way over and then all the way back. That would be one period. But the first time it goes through equilibrium is a quarter of that, right? 1, 2, 3, 4. So a quarter of a period. So what's the period? Well, an earlier question, I had to be reminded that it is going to be 2 pi divided by 16 pi. Whatever value is next to the coefficient on t goes into pi. That's going to be your period of oscillation. So whatever the coefficient is here next to t gets divided into 2 pi. That is your period. But we want a quarter of the period. Well, first of all, let's simplify this. Pi's go away. It's 2/16. That's 1/8 of a second. The period is 1/8. But we want 1/4 of that because they're not asking how long does it take to get back to the starting spot. They want to know how long does it take to get to the first equilibrium, the first time it goes through equilibrium. And that's a quarter of the period. So if I divide this by 4, I end up with 1/32 seconds. Boom. Two blocks are connected to ideal springs and are oscillating on a horizontal frictionless surface. Block A is a mass m, and its motion is represented by the graph as a position is a function of time, shown above at the left. Block B's motion is represented above to the right. Which of the following statements comparing block B to block A is correct? All right. So some of the things we can tell off these graphs, we can tell the period. Since this is time, the period for this one is this amount of time, which looks like 2 seconds. So the period for this one is 2 seconds. Period for this goes from, say, here to here is 4 seconds. All right, so that's one thing I know. Because block B covers more distance, all right, but the amplitudes don't affect much. So the amplitude, this is saying that because block B has a bigger amplitude, it takes more time. Amplitude does not affect the period for a spring, right? Period of the spring is due to m over k, and amplitude isn't in here. So no, that's tricky because it would seem to make sense, but that's not the case. Because the spring attached to block B is initially stretched to greater distance. That's amplitude as well. Because the amplitude, the spring constant is small. No, no, I'm not buying that either. Um, C, because block B has more mass, whereas it has a slower average speed. Hmm. I would the average speed for both of them is actually zero, right? Like, right? Because there's symmetry in the graphs. I don't know. I wouldn't go. I'm not sure the average speed plays a part here. Because B has block B has more mass, its acceleration is smaller than that of block A at any given displacement for the equilibrium position. All right, yeah, since the springs are identical, they produce the same force at any given place, but F equals ma, the bigger mass, produces less A, so I would go with D. And what's interesting about that is it doesn't really, other than realizing that the period of B is longer, the graphs don't come into play to really get that answer D. So that's a tricky question. An object with mass m is suspended at rest from a spring, the spring constant of 200 newtons per meter. The length of the spring is 0.5 centimeters longer than its unstretched length, L, shown above. A person then exerts a force on the object and stretches the spring an additional 5 centimeters. What is the total energy stored in the spring at the new stretch length? So we're looking at the total stretched from this configuration. So its total distance stretched is 10 centimeters or 0.1 meters. So make sure you convert there. And potential energy of a spring is 1/2 the K value of the spring times that distance stretched squared. So we're going to do 1/2 times 200, that's 100, times 0.1 squared. So we'll do the zero point 0.1 squared times 100. So it should be, yeah, it just comes out to be 1 joule. So we just, in that case, the total stretch is what we want. Not this halfway point really doesn't matter. Um, if they told us that it was stretched 10 centimeters from its relaxed position, then that's all we would need to know. Graph above represents potential energy U as a function of displacement for x for an object on the end of a spring oscillating in simple harmonic motion. Which of the following graphs represents the kinetic energy of the object as a function of the displacement x? So the potential energy in the middle goes to 0. That's when the kinetic energy should be the highest. So I'm definitely looking for a graph where the kinetic energy is at a peak in the middle. So here, here. All right, this technically has a peak in the middle, but there's no way the kinetic energy is constant. It definitely stops at some point. So definitely going to rule out that one. And I'm definitely going to rule out this one and this one because kinetic energy should reach a maximum when potential energy reaches a minimum. Now the question is it linear or does it move like um, does it move like or does it look like a parabola? So let's look at this. The kinetic energy of a spring is equal, its maximum is equal to the potential energy at the top, right? So the kinetic energy at the equilibrium position equals the potential energy, I guess I'll go U, spring, at um, at the sides, we'll say, the farthest away. That means 1/2 mv at equilibrium squared equals 1/2 k amplitude, basically, squared. So the kinetic energy is going to vary as the amplitude squared. This is all kinetic energy, so I should just leave that as KE, because that's what they graph here. So I would say that's still a squared. So I would go with D. Let's see if I'm right. Yes, I am right. It's close. It's a close one. It's a 50-50, but I would go with D. You look at it this way. If this changes as a quadratic, it's got the only place you can lose it is into another, it is into kinetic, and so therefore I would expect kinetic energy to mirror that so that they always add up to the same. So yeah. Board is hung from two springs as shown in the figure above, with the board in equilibrium. Each spring has a force constant of 10,000 newtons per meter. How far will each spring stretch when a person of 50 kilograms sits on the board and the board again comes to equilibrium? All right, so we need to know 50 kilograms is 500 newtons. That's our force. That's our extra force downward. So let's find the distance. If this was just one spring, we could find that and then cut it in half because they're each going to share it. So if I was just doing one spring, this is one way to do it. You could do it a couple different ways. You could simply add the two spring constants. That's another way to do it. I'm going to do it for one spring. So the force is equal to K times the distance stretched. I'm looking for the distance stretched. So the force is 500 newtons. The K, I'm going to use 10,000 and just pretend this is one spring for a moment. So it's going to be 500 divided by 10,000. All right, so what's that going to be? I can cancel a couple of the zeros out. Boom, 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 boom. That's 5 over 100. That's 0.02. Well, let's go 5 over, we got that. It's 5 over 100. It's 1. 5 goes into 120 times, so it's 1/20th. But that's just for one spring. I would expect them to be half of that. So, because that's how far one spring would stretch. I would say half of that is divide by 2, so we double the denominator. So 1/40th of a meter, he says, as he looks at the answers. Yes. So the other way to do this is to say force equals 20,000. Just account for the two springs by adding them. It's fine to do that when they're in parallel like that. X, and then do the same problem, and then whatever you get here is going to be your answer, because you already got that factor of 2 in there. And this will come out to be x equal 1 over 40 as well. Here I got 1 over 20, and then I had, because I just considered it for one spring, and then I cut it in half, or in other words, multiplied the bottom by 2. Block of mass 3 kilograms is hung from a spring, causing it to stretch 12 centimeters at equilibrium, as shown above. The 3 kilogram block is then replaced by a 4 kilogram block, and the new block is released from position shown above, at which the string is unstretched. How far with it? Okay. All right. We need the spring constant. So the first thing we're going to do is find, this is a longer problem. So the first thing we'll do is find the spring constant using this fact, and that is 3 kilograms. So the force equals kx. It held 30 newtons. Don't know K, but it stretched 0.12 meters in doing that, 12 centimeters. So I'm going to do 30 divided by 0.12. It's 250. So the spring constant here is 250 newtons per meter. Now, if we take it and release it from here, this spring is going to stretch, and it's going to stretch until, this is the tricky part because we're releasing it. So if we call until that spring potential energy, well, let's just see. If I Yeah, let's just say that if I let it go, it's going to go until, because at that equilibrium position, not equilibrium position. See, there's where what we don't know. Okay, here's what we can do. I don't know if this is the best way to do it, but we're going to find it. Where would this thing stretch to if we didn't let it go, if we let it ease down and we stopped it and we just let it hang at its new equilibrium position? So that would be um, 40 newtons equals 250, the spring constant, times x. That's going to be 40 divided by 250. 0.16, but it's x is not 0.16 though. That's the new equilibrium position. It's going to blow right through that another 0.16. Right. Because then when it comes back up, it's going to go back to this point right here. This is 0.16 away from the equilibrium position. It's going to stretch another 0.16 down here. So I would say 0.32 is the right answer. Yes. So once it's done moving, once it starts its motion, this will be one end up here at the top. This will be the other end. This is the equilibrium position. This is the position it would be in if you, instead of just releasing it from here, let it settle and held it and let it just settle here. That's the equilibrium position. So that's the one that's going to blow right through here and go the same distance away from it this way that it went from here to here. It's going to go here to here, which is why from here to here is double the amplitude. It's double that, 0.16, doubled. Pendulum illustrated above has a length of 2 meters and the bob is a mass of, who cares, 0.04 kilograms, right? Because mass isn't going to probably make a difference, but we'll just run with it. Maybe they want kinetic energy or something. It's held at an angle of theta shown where cosine of that angle is 0.9. The frequency of oscillation is most nearly. Okay, so we can find the period. The angle cosine part, I don't think makes a difference. Because the period for a pendulum is 2 pi length of the pendulum divided by g. I know g, check. I know the length, 2 meters. So I can find the period. And what I remember is frequency is 1 divided by the period. They're reciprocals of each other. So let's find this period first. Period's going to be, let's see, they let us use 2 pi. So L is 2 divided by g. 2 divided by 10 square root, well, that's 0.2. So it's going to be 2 pi times the square root of 0.2. And it's going to be 1 over that. So it's going to be 1 over 2 pi square root of 0.2. All right, and then they rationalize the denominator, which was, I was afraid they did that. This is a math thing, it's stupid, but I'm just going to do it anyway. They multiply top and bottom by 0.2, square root of 0.2. That makes this 0.2 times 2. Oh, are you kidding me? All right, it's cool. Okay, so, wow. All right, if you got this far, you're in good shape. This is some math garbage that they do here to simplify it, but square root of square root of 5 is the same as 1 over the square root of 0.2, I believe. And that's where that comes from. I can double check that, but yes, because 0.2 is 1/5. Yeah. So this right here can be replaced by the square root of 5. And somehow that is important to physics. I hope you get the sarcasm in my voice. Yeah, that's crap, but it's E. It doesn't matter on the mass at all. You will not get a question like this on the current exam. I can promise you that. It's not a bad question. I can see them asking you for the frequency, but they won't hide the answer like this. They'll give it to you in such a way that it'll be, as long as you're good at flipping it upside down, you recognize that, you'll be fine. All right, last one. An object of mass m is attached to a spring in a frictionless inclined plane that makes an angle theta with the horizontal shown. When released from rest, the spring in its unstretched position. All right, its displacement from the unstretched position is x. The object subsequently oscillates about an equilibrium position at a displacement x sub 0 from the unstretched. What is the spring constant of the spring? All right. So x sub 0 unstretched position of the string. But somewhere halfway in between here is that equilibrium position. So this, yes. So this is x0. This is x0. This distance right here. Here, we'll do it in red. So this distance here, or this distance here, is x sub 0. Okay. And they want the spring constant. So the force, say down here, let's see. Well, okay, when it's at this position, if you just set it here, it would be in equilibrium. And if it was in equilibrium, that means the force down the ramp, which would be mass of the object times g times the parallel with the theta would be sine. That force would equal the spring, which would be at, the spring's force at that point would be k x x0, the distance it stretched from its unstretched position to there. So this equals this at your equilibrium position. So that means k would be mg sine theta divided by x0. I'm going with E. Let's see if I'm right. Yes, I am. All right, so here's just to recap. It's all about the equilibrium position, which would be halfway between the unstretched position, this is without any weight on it at all, and where it stops if you let it go from here. Halfway in between is this position x sub 0, where this is x sub 0, the distance from unstretched spring, right? So just the spring, no mass on it. That's this location right here. This would be the location if you attach the mass and let it slide down and kept your hand on it and then steadied it, and it fell and stopped at a spot which was nice and comfy for it. At that spot, the weight portion, right, the parallel portion pulling it down the ramp, would equal the spring's pull up the ramp, which is why I can set these equal to each other and solve for k.